Hello, algebra class. This lesson is going to be our last lesson in our unit on exponential functions. The name of this lesson is Representing Exponential Decay. On your screen, there's a warm-up question involving table A and table B, and using any patterns you notice in this table to help you finish the table. I do want to point out the table goes 0, 1, 2, 3, 4, and then jumps to 25. So you're going to need that pattern to help you figure out what 25 is. Go ahead and pause the video now to see if you can figure out that pattern and what those missing numbers would be. In the first table, the pattern we need to notice is that each time in our table, we are adding a number. Specifically, we are adding 7.5 each time. Now, noticing that pattern is going to help me figure out this next one here. All I've got to do is 25 plus 7.5. That would be 32.5. But to get to 25, I don't want to have to keep adding 7.5 again and again and again and again until I get up to that 25th value. And so instead, we can think about this a little differently. When we get to that 25th time, how many times have I added 7.5? Well, I would have added 7.5 25 times at that point. And what were we starting with in this table? Well, we were starting with that 2.5 there. And so this math right here would help me get that final missing value. We can go ahead and calculate it, but the goal here is to see that we can use this pattern to help us come up with this expression here. So 7.5 times 25 would give me 187.5. And then when we add in 2.5 to that, that's going to give us 190. You could have even come up with an equation for table A. We could say that y value, it's starting with 2.5, and then we are adding 7.5 for every value of x that we've increased up by. So we get this equation right here. You may have even noticed, because we're adding a constant number each time and our equation looks like this, table A is an example of a linear function. Remember, that's one of the big goals in this class, is to identify if something is linear, not linear. And we've introduced this new second type of function, an exponential function. When we get to table B, you may have noticed table B is a little different. It looks like for this first one, we're also adding 7.5, but then I noticed that's not going to work for these following ones. You may have also noticed it's growing really quickly in table B. We went from 2.5 to 10 to 40 to 160. That growth is happening really quickly. It's happening exponentially. I know it's happening exponentially because if we look at what's happening here in this pattern, this isn't an addition pattern, this is multiplication. We are multiplying by 4 each time. So again, noticing that pattern of multiplying by 4 can help me get to this next one. 160 times 4 is going to be 640. But again, I've got that problem of I don't want to be in my calculator just writing times 4, times 4, times 4, times 4, and counting up to 25. Instead, there's an expression we can write that involves the same two things that we used up here. That expression is going to use what we're starting with. So here it's that 2.5. And then our pattern. Our pattern is we are multiplying by 4. How many times would I multiply by 4? Well, to get to x as 25, I'm multiplying by 4 25 times. Now I can write times 4 times 4 times 5 25 times. Or we can make that a little easier and just use an exponent. Can use that exponent of 25. And now I'm actually going to leave it like this because if you did the math for that, that is a quite large number. But the real goal here is to get that expression again. Notice to get that expression, we need that starting value and also that growth factor, that number that we're multiplying by each time. So the second table here is an example of an exponential function. The table B in this problem is showing an example of exponential growth, but yesterday we had started talking about exponential decay. That word decay lets me know that the values are going down, not going up, like we see in this table. Now, we've talked at this point about what exponential growth looks like in stories, in tables, in equations, in graphs, and we want to be able to do that same thing with exponential decay. And so our goal for today is specifically around graphs. We want to be able to create and interpret a graph representing exponential decay. We saw in the first 3 lessons from this unit that exponential growth looks something like this. If I was graphing it, it's that curved line going up. We want to see what exponential decay looks like. When I ask this in class, usually we've already talked about how that means it's going down, but how is that line going down? Is it looking like a straight line like with linear equations? Is it curved down like this? Is it curved down like this? Which one do you think? By the end of this lesson, we will have an answer. We are going to start figuring out what exponential decay graphs look like using this story right here. One of the goals for this unit is to give you lots of different examples of situations where you could use an exponential function. And so this story here is about algae, which is that green stuff that grows in water. We've got, in order to control an algae bloom in a lake, scientists introduced some treatment products. Those words, algae bloom, just talks about when the algae gets really bad. So if you look at that picture, there's a ton of algae. We call that an algae bloom. And they're trying to treat it. They're trying to get the algae to go away. We are told that once the treatment begins, the area covered by the algae A in square yards is given by the equation A equals 240 times 1/3 to the t power. Time, t, is measured in weeks. This first question, we have done this a lot in this unit. I think we've done it every single lesson. The question is, in the equation, what do those numbers tell us? Specifically, what does 240 tell us about the algae, and what does that 1/3 tell us? Go ahead, pause the video now, and try to answer this question. Starting with the 240, notice that is the number that we're going to be multiplying. This number here always has had the same meaning, and that number right there represents the starting amount. So here, the 240 tells us that's the starting amount of algae. I want to make that a little more specific. Is that like the number of algae? I don't even know how you would count algae. Is it the weight of the algae, the starting amount of algae? Like what? How are we measuring that starting amount? And we're told in the story it's the area covered. So I could say 240 represents the starting amount, beginning amount, initial amount. I'm going to write the initial area covered by algae. You have to say something about the initial or beginning amount of algae because this tells us we're talking about when time is 0. You can't just say it represents the amount of algae because that amount of algae, the scientists are hoping is going to change. They're hoping it's going to go down. That first number there always represents the initial amount. Our second number is 1/3. That's the number we're multiplying by. And we learned yesterday that 1/3 represents the fraction of algae left left or left over. How often? Well, we are told we're talking about weeks. So it's the fraction of algae left after each week or each week of treatment. We have to say something about that's the fraction that's left. And you want to also give that time about each week's. Now, you could also have taken this fraction, and we had talked about those two fractions that you can come up with based on a story. If 1/3 is the fraction of algae left, this also tells me that 2/3 of the 2/3 of the algae is removed each week. So that's the part that's going away because of the treatment. And so you could use either of those fractions to help you see how that algae amount is changing. Now that we have a better understanding of this equation, we are going to go ahead and make a graph. And so this graph, we want to show the algae when t is 0, 1, 2, 3, and 4. Remember, t is the time in weeks. So we're looking at how this algae changes the first 4 weeks. We had done some graphs in the first 3 lessons with exponential growth. I know in class, a lot of us had a lot of success making a table. And so looking at when t is 0, 1, 2, 3, and 4, what that algae area is going to be, and then using that table to help you create your graph. I'm going to have you go ahead and try this on your own. So again, pause the video now and see what graph you can create. As you're working on your graph, it mentions here the scale for the axes. Make sure you're numbering your x and your y axis so that we can see what numbers your points are talking about. Go ahead and try that now. Before I start my graph, I'm going to create my table because it's going to show me what numbers I need on my graph. Now, we had mentioned on that previous slide that the starting amount, so that's time equals 0, the starting amount is 240. I don't even have to do any math for that. I'm just getting that from my equation. After 1 week, I need to figure out what 240 times 1/3 is. And so when you calculate that, that's going to give us 80. For t equals 2, I'm just using my equation. That would be 240 times 1/3 squared. And so to do that, you can use your 80 and multiply it by 1/3 again, or you can go ahead and do this math here. Either way, we are going to get 26.666666. So I'm just going to round that to 26.7. For hour 3, the same idea. If I am using my equation, I need to do 240 times 1/3 cubed. And when you do that, that's going to give us 8.888888. So I'm going to round that to 8.9. And then finally, for hour 4, that's just going to be 240 times 1/3 to the 4th power. And so that, again, you can use the previous number and just multiply it by 1/3 again. But that would give us, it's really close to 3. So I'm just going to go ahead and write 3. These numbers right here tell me what numbers I'm going to need on my graph. My graph is talking about 2 things. Remember, your input, your independent variable, always goes on your x-axis. Here, that's going to be time. And I see for time, we're only going up to 4, so I can really spread out my 4 minutes. I can put 1 here and count every 3 boxes. So 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4. And spread it out like that. You could probably, I think, even spread it out a little more. And then for our y-axis, that's always your output, your dependent variable. And so here, that is the algae area. How fun. And we're seeing the biggest number I need on my y-axis is 240 because it's going down. So that means the highest number on my y-axis would be 240. If I divide that up, I'm going to go ahead and see 1, 2, 3, 4, 5. Make each box 20. 1, 2, 3, 4, 5. That's 200. 1, 2, 3, 4, 5. That's 300. There's many ways you could do this, but the idea is to fill up the graph as much as we can. So something like this is a good example of how you could set up your graph. The rest of this is just plotting these points. So I want my line to start at 240. Here's 200. Each box is 20. So 220, 240. My line is going to start right here. At 1 hour, we see it's at 80. 2 hours, it has an area of 26.7. 3 hours, it has an area of 8.9. And then by hour 4, it's down to 3. So looking at those purple points, I can start to see what our graph might look like. Something like this, maybe. So looking at this, we have an example now of what exponential decay would look like. And this is going to be true for a lot of exponential decay graphs, is when we kind of were thinking about our different options, it's not going to be a straight line. Those are linear equations. It's not going to curve like this. It's going to curve that other way. So if you were thinking it was this third one, congratulations. We're seeing that first time when you take our algae and you remove 2/3 of it and leave only 1/3, that means that first week a lot of the algae is disappearing, and then it's still decreasing over time, but decreasing less and less. So this right here is a graph that goes with this equation. Some questions for us to think about using our graph. Got these 3 questions here. Again, I would encourage you pause the video and see what answers you can come up with for these 3 questions. All right. So that first question's asking about what would it mean if t was 2.5? Well, remember t represents our weeks, and t equals 2.5 would mean we're talking about 2.5 weeks. You know, there's going to be some change between week 2 and week 3. And so you could look at like halfway through the week what that algae area would be. It goes into the second question, how could you estimate that? We could look at our graph. Instead of 2 and 3, I could look halfway, which for my graph, it's right here, and use that to estimate. For my graph, it looks like maybe around 20. If we had a more professionally done graph, it would be a little easier to estimate, but I'm sure it's around 20. We've got someone says that after 7 weeks, the algae will disappear. I'm curious what you all said for this one. If we continued our table by week 5, it would be down to about 1. By week 6, it's going to be down to 0.3. By week 7, it's down to 0.0. What am I doing? 0.09. And so we see it's definitely going less and less, but it's not going to be completely disappeared. If we keep multiplying by 1/3, 1/3 is never going to give you an answer of 0, right? If you're to get 0, you would have to multiply by 0. Now, in reality, if there's only 0.09 square, what are we measuring? Square yards, it's basically like it's gone. So in real life, someone might come out and say like, okay, all the algae's gone. But this idea of multiplying by a fraction again and again and again, it's not actually going to give us 0. It's just going to give us really, really tiny numbers. So what you see on that graph, which we can kind of see on ours after week 4, right, is it's going to get really, really flat. The line's going to get closer and closer to 0, but it won't ever go past 0 because you can't have a negative area. To help us understand these graphs of exponential decay a little more, I've got another question. In the second question, we're going the opposite direction. We do this for everything, right? So instead of me giving you an equation and you coming up with a graph, we want to be able to go both ways. So that means we want to be able to look at a graph of an exponential decay function and then come up with what the equation would be. And so to help us talk through that second part, we've got this graph right here about insulin in the body. This is not just true for insulin, but any sort of medication, that when you consume medication or insulin in your body, that amount of insulin or medication in your body is going to decrease with time. And we can represent that relationship with an exponential function. Go ahead and read this situation now and look over the graph and see if you can come up with any observations from our graph to help us get ready for the second question. So some of the observations you could have made from the graph is that the insulin is starting with 100 micrograms, that we see it's decreasing over time. It looks like it's not linear. This is not a straight line. It looks like it's curving very slowly. The first question we're looking at is how much insulin broke down in the first minute, and what fraction of the original insulin is that? So if we go to our graph at minute 1, we're given the coordinates for the point. This is at minute 1, the insulin is at 90 micrograms. So if we started with 100 and after 1 minute there's 90, how much insulin broke down in the first minute? Well, it looks like we lost 10 micrograms. That's how much broke down. Now, if we continue to kind of look ahead, I noticed 10 micrograms broke down in the first minute, but that isn't true for future minutes. We're going, if it was, it would say 190, 280, 370, and we're getting different numbers there. So this pattern here isn't going to be subtracting 10 micrograms every minute. It was just 10 micrograms in that first minute. The second question, though, what fraction of that was broken down? We've got, 10 micrograms broke down out of the total we started with 100. So that would be the fraction 1/10. 1/10 of the insulin broke down from minutes 0 to 1. Continuing to look at that, the next question is how much insulin broke down in the second minutes? Well, from minute 1 to minute 2, and I'm going to label it, we're looking at from minute 1 to minute 2, we went from 90 micrograms to 81 micrograms. How many micrograms did we lose? Well, we lost 9 micrograms. And as far as the fraction goes, 9 micrograms out of, what did we start with at minute 1? Not starting with at the very beginning, but at minute 1, how much insulin did we start with? At minute 1, we were starting with 90 micrograms. So in this 1 minute, we lost 9 of the 90 micrograms. And if you simplify that fraction, where our fraction's made up of how much we lost and then the total, that gives us the fraction 1/10. So continuing with that pattern, if we continue to look at the fractions that are lost after each minute, I could do the same thing looking from minute 2 to minute 3. We went from 81 to 72.9 micrograms. So that would be 8.1 micrograms out of our total. How many total micrograms of insulin did we have at the start of minute 2? We had a total of 81. And again, we're getting that same fraction of 1/10. So 1/10 is what our pattern is. We're seeing we're not subtracting the same amount each minute, but we are seeing what fraction is going to be there. Or sorry, is we're going to lose. So the question for what fraction of insulin remains in the bloodstream? Well, if we are losing 1/10 of the insulin, that means what fraction remains? What fraction is left over? Well, similar to what we did yesterday, 9/10 must be what's left over. 1 plus 9 is 10. So we're using all 10 parts there. If 1/10 is lost, 9/10 remains. So 9/10 is that fraction that represents how much insulin is remaining. Being able to figure this out is huge. I know so many of our students say they want to go into the medical field, become nurses, or do something with medicine. Um, no, understanding how medication works in your bloodstream and how much medication is left in the bloodstream is really important for that profession. We're going to take this to one last part here. So using this observation, we can then come up with an equation to represent this graph. So that last question, our favorite question, is what equation could we use to express the milligrams of insulin in the body, which we're going to call L after m minutes? Well, if we wanted to write, oh, that must be the letter I for insulin. If we wanted to write an equation to represent how much insulin is in the body, again, one of those numbers we always need to help us write these equations is the number that represents how much insulin we are starting with. So that was given to us in the story, and then we also talked about at the beginning. That's this number 100 here. I'm finding it on my y-axis. It's our y-intercept. So my equation, we're going to say, well, we're starting with 100 micrograms. And then if I want to write an equation to show how much insulin is in the body, we've come up with two different fractions we could use to talk about the situation. But if I'm talking about how much insulin is in the body, I'm talking about the second fraction here. If I wanted to know how much insulin is in the bloodstream, I'm taking my 100 and I'm multiplying it by 9/10. I'm multiplying it by that decay factor to see how much insulin remains over time. And I would multiply it by 9/10 every single minute that passes. That was that pattern we were seeing. So I'm going to say I'm going to multiply it by 9/10 m times, because that's happening every single minute. And so this right here would be the equation we could use to represent this situation. If you are given a question to write an equation from a graph, where are we getting these numbers? Well, we said 100, I can see that on the graph as my y-intercept. And then that 9/10, that took a little bit of calculating, right? That was this fraction we were calculating, looking at how much insulin had left. So from 100 to 90, that's 10. That's decreasing 10 out of our total 100. And then we did it a couple times just to confirm we had the correct fraction. So I've got one last question here for you to practice applying what we just saw. I have to back up a little bit so you can see everything. So continuing with this theme of medication, we've got acetaminophen. The graph is showing us the milligrams or micrograms of the medication in the bloodstream again, but this time we're talking about our time in hours. If these three questions for you, go ahead, pause the video now and check to see how well you understand this by answering these three questions. Coming back to see how you did. For question 1, what is the vertical intercept? Our vertical intercept on this graph, that y-intercept, is at 1,000. So one of the things you needed to tell me is it is at 1,000. What does it mean in this situation? Remember, your y-intercept is that always that starting amount. So here it's telling us the starting amount of acetaminophen is 1,000 micrograms. Um, so I'm guessing that's like the dose that the patient took at the beginning. That was the starting dose, the starting amount of medication. For that second question, we've got what fraction of the medication remained after 1 hour? This is where we get to set up that fraction. I'm going to put my work up here. So from minute 0 to minute 1, how much was lost? Well, we went from 1,000 micrograms to 750. That means we lost 250 out of our total 1,000. And so if you simplify that fraction, that is the fraction 1/4. And we could check that by looking at the future hours, but it's correct. 1/4 represents the fraction lost each hour. But notice number 2, it's not asking about the fraction lost each hour. It's asking what fraction of the medication remained. So if we're losing 1/4 of the medication, that tells me 3/4 remains each hour. And so the answer to that second question, we're talking about what fraction remains. That's 3/4. Question number 1 and question number 2 are there to help you with question number 3, that final question. And one of the more important questions, I think, from today is if you get a graph, can you write an equation? We want to be able to do that for all types of functions. And so if you've got these numbers, you've got most of the things you need at this point. We want to say the amount of medication in your system after T hours. Well, we're starting with 1,000 micrograms, and 3/4 is the amount that remains after every hour. And so we get this exponential function here. This is the final lesson from our unit on exponential functions. The goal from this unit is if you have a situation, a graph, an equation, can you understand and interpret and write these exponential equations? So basically being able to like switch from all of these things. If I give you a situation that's exponential, could you come up with an equation? Could you come up with a graph? If I give you a graph like I did here, do you understand the situation? Can you come up with an equation? We want to be able to switch between those different mathematical models. Exponential equations can look a little crazy because they've got those exponents in them. But hopefully you're feeling a little more confident than you were at the start of this unit. Remember, we're always here to help. So if you want to go over extra examples or you have any questions, please reach out. Thanks so much for watching.